Hey everybody, welcome back to our AP Calculus AB course videos. And in this one we're going to cover three concepts as you can see on screen. So we'll do some examples of the first two, which are theorems, and we'll just skim the third one, which will be explored much more in the next video. So these are two theorems you should be learning in your first limits and continuity unit. Now these two theorems are the squeeze theorem and the intermediate value theorem. So what we're going to do is we're going to explain or define these theorems, and then we'll go through maybe like a couple of examples. So for the squeeze theorem, let's say you have three functions where your function h of x is less than or equal to f of x, which is less than or equal to g of x. So you'll have these three functions, and they're all in the same interval. So we'll call this interval a to b, where there is some c within this interval. So there is some c within the interval AB. One second. Okay, so there's some c or some number within that interval AB. Now, if you're given these next couple specific pieces of information, you can find out a limit of f of x. So if you're told that the limit as x approaches c of h of x is equal to the limit as x approaches c of g of x, well then you know that the limit as x approaches c, so we'll call this a. So a is going to be that limit as x approaches c of h of x, which is the same as x approaches c of g of x. So in this case, the limit as x approaches c of f of x will also be equal to a. And now mathematically this makes sense, right? So if h of x were to be 5 here and g of x were to be 5, well, f of x has to be 5. So now keep in mind, questions regarding the squeeze theorem will not be this simple. You will have to prove that the limit exists for h of x and g of x, and then you'll have to prove that they're equal. So when you prove the limit exists, continuity, things like that, you require different steps in doing so. But this squeeze theorem actually gives us a couple of special trigonometric limits. So the two special trigonometric limits we're going to learn now are these. Whoops, accident right there. But the first one is going to be the limit as x approaches 0. So keep in mind these limits exist by this squeeze theorem. So the limit as x approaches 0 of sine x over x is going to be equal to 1. Second one, let's see if we can fit in some space here. Our second limit, so the limit as x approaches 0 of 1 minus cosine x over x is also going to be equal to, is going to be equal to 0. So just take a note of these. So these are going to be two special trig limits that you'll learn. Now, if you look at them, well, why do you need special trig limits to evaluate these? Well, if you just plug in 0 right now, what do you get? You get sine of 0, and if you take a look at your circle, your unit circle, well, sine of 0 is just going to give you 0, and you get 0 over 0, and that's indeterminate form. But using the ways we have learned so far, such as rationalizing or factoring out, or just substituting it in, none of those actually help us get rid of our indeterminate form. So through the ways we've learned so far, we would be stuck where we are right now. We wouldn't be able to determine what the limit is or whether it exists with those methods. Hence, the squeeze theorem helps us provide a way of doing so, but we'll learn a future method that's called the L'Hopital rule. That method will help explain why this and why these two limits actually algebraically make sense. Now if you do the same thing here, well, 1 minus cosine of 0 is 1, so you're going to get 1 minus 1, which is 0 over 0. And same thing as the sine x over x limit, we don't know how to get rid of that indeterminate form yet. Okay, great. So moving on to IVT. So IVT is short for intermediate value theorem. And this theorem is one that will probably be used a lot more than the squeeze theorem. So the IVT states let's say you have a function f of x. So if if your function, we'll say f of x, is continuous, or cont for short. So if this function given is continuous on your closed interval a to b, so okay, quick tangent, sorry. So when you have square brackets around an interval, that means it includes a and b. For example, anything from 0 to 1 in these square brackets would be including 0 and 1. But if you have the parentheses, this is excluding 0 and 1. So start at like 0.0000001, like, you know, that type of number. So that's just to give you an idea. But if f of x is continuous on this interval a comma b, now if f of a is not equal to f of b, so these are two separate conditions that have to be fulfilled. And let's say you're given a number c. So, and c is between, c has to be between f of a and f of b, and f of b. So if these three conditions are fulfilled, then we're going to know that there is at least one number. So there is at least one number, we'll call that y. There's at least one y in this interval a comma b. So keep in mind that this has to be the closed interval, such that f of y is going to give us the c value. So what does this mean? Well, if you think about it, you'll have a function that's continuous. Now, you know, let's just we have some space over here, so probably won't need some of this down there. So let's say we have some type of function here, like that. Now we don't know the equation, but we know that this function is continuous. We don't have to prove it in our scenario, this is just for an example. But let's say we know this function is continuous on this interval. Now we know that your endpoints, so this is f of a and this is f of b right there. So actually, let me put that here. This is f of a and this is f of b, and that gives you your interval a comma b. Oops. Okay, so we know that f of a is not equal to f of b. Now let's say we're looking for a 0, right? So we're looking for this dot right here. So c, let's say c is equal to 0 in this case. Well, you know, we know that f of a is less than 0, and f of b is greater than 0. And that's just given to us by the graph. So we're going to know for a fact that there's one value within this AB interval where our f of x function gives us 0. And now that actually makes sense. So this IVT is going to be pretty often used to confirm whether a function has zeros. So this gives you an idea of what you would do in that scenario. You have to make sure that your c value, which in this case would be 0, is between your endpoints, and then you can, by using IVT, confirm that that function has a 0. Instead of, you know, wasting time trying to plug in or whatever. And some AP questions will actually ask you to just prove whether this has a 0 or not. Great, so now that we've covered the two main theorems in this unit, we're going to take a minute or so to skim on the topic of infinite limits. Now, in one of the earlier videos, I said that when you have a limit like this, where it's approaching some random, really large value, we can't quantify it. We would just count this as an infinity, right? Whatever limit it would become would just be infinity. Now, there is a concept of infinite limits, and in some cases, they can actually be simplified. So let's say, just to give you a really quick example, so I'll expand on this in the next video, but just to give you some food for thought. So let's say we have the limit as x approaches infinity of 4x squared over 5. Now I'll go through really quick examples. So limit as x approaches infinity of 4x over 5x, and limit as x approaches infinity of 4 over 5x squared. So I'm going to give you guys the answers for these three problems, and in the next video I'll go ahead and explain why the answers are like this. So for the first one, this limit's going to be infinity. For the second one, this limit will be 4/5, and for the third one, this limit will be 0. So you have the answers here. Feel free to pause or come back to the video and try to solve it on your own. But if you're still stuck, go on to the next video and I'll go ahead and explain the concept of infinite limits. Now, we'll also be using some theorems like IVT and squeeze theorem when it comes to infinite limits.